All right. So then, as I was saying, if we verify the hypotheses of this John-Nirenberg lemma, then that tells us that the BMO norm is actually controlled by up to some constant times this n. Okay? All right. So now, to this end, we're now going to fix a cube QR, which will have center, let's say at x tilde t tilde. Those will be fixed points from now on. This is contained in Rn. We're going to lift it up to sigma. So what do I mean by that? Of course, sigma is not necessarily always lying above this this hyperplane, but it makes the picture easy to draw it that way. So here's QR down here. And I lift up, and I form the elongated IR. Okay, where the center is obtained by lifting the center of this guy up. All right, and then delta R is the intersection, and of course the center, since we're lifting up to the graph, is going to be at A of x tilde t tilde, comma x tilde, comma t tilde. Okay? All right. And then I'm going to set delta star to be the same center with side length m times r, where m is going to be, let's say, 1,000 times our usual constants, m naught times the square root of n, times eta to the minus 1, where eta is the constant in lemmas 2 and 3, which are these Caffarelli-Salsa lemmas. Remember, there was the conclusion in lemma 3 was that there was some height, eta times the scale r, that we had to cut off. And below that, then we had the comparability of the vertical derivative of the green function with g over the distance to the boundary. Okay? So then we're going to define f star as in lemma 6, the one that we just proved a little while ago, relative to this guy, relative to delta star. All right? And I'm going to set f to be pi of f star, and pi is the projection that you think it is. Pi of y naught, y, and s is just y and s in Rn. It projects down to Rn. All right? So then we have that QR minus f, the measure of that, is less than or equal to pi, the measure of pi of delta star minus f star. Okay, because delta star is a much fatter version. And since Hausdorff measure does not increase under a projection, this is less than or equal to the sigma measure of delta star minus f star, which is less than or equal to epsilon times the sigma measure of delta star. That was the content, or part of the content of lemma 6. And of course, this is an all fours regular measure, so up to this dilation factor that depends on m, this will be less than or equal to epsilon times this Lebesgue measure of QR. Okay, so QR minus f is still a very small portion of QR. We take the epsilon small. All right, so then we do the usual, the obvious thing that if we look at the set of YS's in QR, such that dNA of YS minus a constant is bigger than n. We use Chebyshev's inequality. This is going to be less than or equal to 1 over n times the integral over f intersect qr of dna minus c, plus then just the measure, just crudely dominate the other part by the measure of qr, or sorry, by the measure of the complement of f, which is at most this. Okay. All right. So if we first take, remember, what are we aiming for? We're aiming to get this some sufficiently small portion of the full measure of QR, right? To get this set that small, okay? So by taking first epsilon small enough, and then n large enough, we can see that it's enough to prove that there exists a constant C depending on QR, such that, what do you think happens? That this thing is bounded by the measure of QR. Okay. So such that the integral of intersect QR of dn of a minus c is less than or equal to some constant times the measure of QR. The constant will depend on all the hypotheses. It will depend on n, m naught, the infinity conditions for the caloric and adjoint caloric measures. And it'll depend on this epsilon, but eventually we've fixed the epsilon. Okay? All right. And then we take n big enough to compensate for that. All right, so this is what we've boiled things down to. And now the first step to doing this is a localization. Because, of course, this half-order fractional derivative is not a local object. So we want to localize it. This won't be hard. So we're going to let capital phi be in C0 infinity of, let's say, the interval from -5 to 5. It's going to be a nice smooth bump function, identically 1 on the interval from -4 to 4. It's always between 0 and 1. We're going to take it to be even. And then we're going to set phi r of ys to be defined to be capital phi of the parabolic length of ys divided by r. Okay. All right. And so then let's recall that dn is a time derivative composed with a parabolic fractional integral. So I'm going to call this thing, for convenience, I'm going to call this I parabolic. So a parabolic fractional integral. Okay? And so it has a kernel. Let's call it capital V of xt, satisfying capital V of xt is less than or equal to parabolic norm of xt to the 1 minus d. Okay, it's exactly analogous to the first order fractional integrals. This just comes out of homogeneity. Okay, all right, and then I'm going to set VR to be V times phi r. So it's sort of a smoothly truncated localized version of this guy. Okay. All right, and so then I'll let I parabolic with a superscript r denote the truncated or localized fractional integral. Let's define it like this. It's going to be this truncated kernel convolved with G. And again, it's a full space and time convolution. All right. Just as V is the convolution kernel for the original fractional integral. Okay. All right. And then I'm going to set dnr to be the localized version. Remember, the dn itself was dt composed with I par. So this is going to be dt composed with a localized I parabolic r. Okay. And I think to save time, I'm going to ask you to believe me when I tell you that it's not hard to see that if we choose C to be, I have to define what this is, ER of A of x tilde t tilde. Remember, x tilde t tilde is the center of QR, where ER is the error, dn minus dnr. Okay, so it's the non-local part. All right, it's the part where instead of having phi r, we have 1 minus phi r. Okay. All right. Then it's not hard to show that dna of xt minus c, which is, or sorry, not dna, ERA, equals ER A of x tilde t tilde. That's not what I meant to write. ERA of xt minus ERA of x tilde t tilde. This is going to be just bounded by a uniform constant, depending on the usual suspects. Okay, and that's because, remember, the kernel of this guy is dt times this business. And so it satisfies Let's call this kernel, oh, I don't know, KR. How about that? All right. It's going to satisfy the following bounds. The first one is that KR of xt is less than or equal to the parabolic length to the minus d minus 1 power. We had 1 minus d, and then we're hitting with a time derivative, which is like differentiating twice, times the indicator of this set where the length of xt is, say, bigger than 4r. All right, that's because that's the nature of the phi. Second, if we look at kr of xt minus kr of x tilde t tilde, this is less than or equal to, for xt, in QR, which is where we're going to be integrating. This will be bounded by, well, we just use the smoothness here of this guy because it also has, right, it also has a Lipschitz, parabolic Lipschitz bounds. This will be, and the difference, the distance between xt and x tilde t tilde is like r. So this will be like r over xt plus r to the d plus 2 power. Okay.
Steve, could you recall what is D is the dimension of the space, or
D is the homogeneous dimension. D equals n plus 1 is the homogeneous dimension of parabolic Rn.
All right, thank you.
Sure. Okay, and the last property is that ER of 1 is 0. ER kills constants, and it's because it involves this t derivative, right? It's the kernel is dt of this thing. Okay? All right, and you put those ingredients together, and it's easy, right? This allows you to subtract off an appropriate thing from A, and then it's easy to see that you get this. And consequently, if we integrate on QR of ER of A minus that particular choice of constant, this will be bounded by the measure of QR, which is what we're after, okay? I guess it was ER with a superscript. Okay, so consequently, it's enough to prove the localized version, I guess it's not on the board anymore, but the localized version of the estimate that I wrote earlier, okay? So that the integral over f intersect QR of the localized half-order derivative is bounded by the measure of QR. Okay, it's enough to do that. And at this point, having localized, it's the usual kind of thing that you do when you're doing Calderon-Zygmunt theory in BMO. The local piece, you usually don't have to subtract a constant. The constant is to give you cancellation for the far away part. Okay? All right, so now let's recall that I've normalized I've defined a normalized caloric and adjoint caloric measure. In particular, the caloric measure was normalized this way. It's a normalized version of caloric measure at the time forward corkscrew point relative to delta star. And that delta star is delta MR centered here. Of course, this is on the boundary, so x naught tilde is A of x tilde t tilde. Okay? So I'm going to set G, oh, and M was a special M, right? M was 1,000 M naught root n times eta inverse. Okay, so I'm going to also normalize the green function. I'm going to set G to be the same normalization. I multiply by sigma of delta star, and it's going to be G with pole at this time forward corkscrew point. And the variable, I'll view it as the adjoint variable. So this is now an adjoint solution. At least for S less than the time value here. Okay. All right, and now this brings us to really what the heart of the matter is, what really the heart of the proof is about after all these preliminaries. Okay. So, given R positive, although it'll be less than or equal to this ambient scale capital R that we're always working with, we're going to let sigma R denote the level set for G, for this normalized green function. Okay? The level set at height R. Okay? So of course note that sigma naught is the original boundary, or really the original boundary where the time coordinates are less than the time coordinate of the corkscrew point. Okay? So then by the adjoint version, of lemma 3, that was the concluding one of the Caffrelli-Salsa lemmas. We're going to apply it with u equals g, and what we get is that the vertical derivative is like g over the distance to the boundary. Okay? So we get dg dy naught at a point y is going to be comparable to g of y over delta of y in, let's say, omega 100r, which is going to be, in other words, I 100r of the same center that we've been working with, x naught tilde, x tilde, t tilde, intersect omega. Okay, and we can say that because that's why I chose for the really fat guy, the delta star. We have this dilation factor by m, and the m includes an eta to the minus 1, where the eta was the constant in lemma 3. So we get to say this. Okay? So in particular, so now from now on, we're always going to be staying inside of here. So where we have these good things. So notice what this says. In particular, of course, this is always a positive thing. All right? So therefore, G is strictly increasing in the y0 variable, in the vertical variable. Okay? And hence, sigma r, each level set is actually a graph inside omega 100r. Okay? All right? So, in other words, we have that sigma r, lowercase r, intersect omega 100r is equal to a graph of a function a sub r of xt with xt in q100r. Again, with the same center as before. Okay? All right. So let me just introduce a bit of notation that we're going to find convenient. So I'll often write a of r xt to mean a sub r of xt, right? Because we're going to be often differentiating in the r variable. Okay. So let us notice that, of course, a of 0 xt is just our usual graph function that forms the original boundary. Okay. All right. And I'll sometimes also write, for just shorthand convenience, capital psi of rxt to mean the point a of rxt comma x comma t. Okay? All right. So just to recapitulate everything that we've just said, we have that g of a of rxt xt equals r when xt is in q100r of x tilde t tilde. Okay? All right. So at this point, I'm going to set h naught of ys to be the distance from ys to f. Remember, f was the projection of this set f star up on the graph. And I'm going to let h of ys be the regularized version of this guy. The regularization of h naught as in lemma 4. Okay? Now there's an important lemma for us, lemma 7, which says the following. It says that, right, I've got this function a of rxt, whose graph defines the level set. So if I allow a variable contour, right, I'm going to allow the R variable to range along the graph of H, okay, or along H. All right, and I subtract A of ys. It's going to turn out that this is comparable to H of ys with constants dependent on all the allowable stuff. All right, it's not quite saying that A is Lipschitz in this variable, right? This is A of z, right? Because this is the same as A of 0 ys. It's not quite saying that A is Lipschitz, but for our purposes, it's close enough. Okay? All right. So let's do the proof of this. I think I'll have time. So first of all, notice that if ys is an f, then remember h is comparable to h naught, which is the distance. So then h of ys equals 0, and the result is trivial. Okay, so the only non-trivial case is when y and s is not enough. Okay, so in this case, we choose a point xt in f that actually achieves the parabolic distance, such that the distance from xt to ys is exactly equal to the distance from ys to f, and hence is comparable to h of ys. Okay. All right. So now for convenience of notation, I'm going to set capital Y to be the point on the graph, A of ys, ys. I'm going to set YH to be the one where we've lifted it up from 0 to height h of s, h of ys. So this will be A of h of ys, ys, comma, y and s, right? This is the vertical coordinate. All right. And then I'm going to set capital X to be the point on the graph above xt. Okay? Of course, notice that this one is in omega, since by assumption, h of ys is strictly positive. We're away from f. All right. So now by doubling of the caloric measure, if we're given a number gamma strictly positive, less than or equal to 1, then for all rho bigger than or equal to gamma h of ys, which again, that means is comparable to gamma times the distance from xt to ys. Then we get that the average over delta rho centered at y of k star is comparable to the average. Of course, this constant will depend on gamma, but that's okay. The average on delta rho of the point capital X But lemma 6, remember, says that that's like 1. Right? Because for points, because if xt is an f, then this capital X is an f star. Right? And lemma 6 told us that all the averages on surface cubes centered at points in f star are like 1. Okay? All right. So then, for n large enough to be chosen. Oh, and by the way, I'm sorry. There was that earlier n in the John Stromberg lemma. This is a totally different n. That was n is defined locally. Okay? I'm going to set omega tilde to be defined to be, so this is really, I guess you could call it omega tilde centered on this point y here. This is going to be omega intersected with the parabolic box at scale h of ys over n centered at y. Okay? So then if z is an omega tilde, if I held our continuity at the boundary, the adjoint version, I get that g of z is less than or equal to, up to some constant, delta of z over the scale h of ys to the alpha with g being evaluated at the corkscrew point relative to the scale h of ys. Since this is an adjoint solution, it'll be the backward corkscrew point. And here I'm using implicitly, along with Heller continuity at the boundary, I'm also using Carlson's estimate. And this is relative to the point y. Okay? So I take the backwards in time corkscrew point relative to this point for this scale. Okay? Which is a positive scale. All right. And I see that notice that for z in that box, the distance from z to y is like h of, at most, h of ys over n. So I pick up here n to the minus alpha, and then I'm going to use CFMS the scale here is h of ys, so I divide and multiply by the scale. When I divide by the scale, I pick up the average of harmonic measure at that scale, or caloric measure at that scale. Okay? So this will be less than or equal to n to the minus alpha, h of ys, average on delta h of ys of k star. So that's the surface box centered at y of this radius. And again, this is comparable to 1 by star. Okay? Or sorry, this, I should say. This part is comparable to 1 by star, and hence this is less than or equal to n to the minus alpha h of ys. Which if we take n large enough is going to be less than, say, 1/2 h of ys. Okay? But on the other hand, by definition of the level set, we've got that G at the point YH is H of YS. Because this is the point, right, where the R value is H of YS. That's the definition of the level set, which of course is obviously strictly bigger than 1/2 H of YS, which tells us that the point YH cannot lie inside omega tilde. All right. Which means that, and since Y itself was sort of the central base point for omega tilde, that says that the parabolic distance from YH to Y is got to be bigger than or equal to H of YS, depending on n, but we fixed to n. Okay? But notice that YH and Y lie vertically one on top of the other. So the distance is just the vertical distance. Okay? So this says, and of course the vertical distance to a Lipschitz graph is comparable to the actual distance. So this tells us that, and I'm going to call this triple star, I think, yes. Delta of YH is comparable to A of H of YS. YS, comma Y, comma S, minus A of YS, which equals this, and hence this is bigger than or equal to H of YS. Okay? Because this is same as this, which is bigger than this. Okay, so that's one direction, right? Because we want to show actual comparability. And if you'll indulge me for just a couple of minutes more, we'll do that. This won't take long. Okay. All right, so this proves one direction. And now we need to get the opposite inequality. So now we look at the ratio H of YS divided by A of H of YS, YS minus just A of YS. Of course, ultimately, we want to say that the ratio is like 1. All right, that's what we're trying to prove. So from what we just proved by triple star, or one thing we just observed, part of triple star, not the major observation, but just a simple-minded observation, is that this is the same as H of YS over delta of YH. Okay? But remember, by definition of the level set, H of YS is the same as G at this value. Okay? And now we get to use CFMS. And this is like the average of K star with respect to the surface ball at this scale, this radius, and with center at y. Okay? But this scale, notice what we showed about this scale. This scale is bigger than or equal to h of ys. That if we take rho to be exactly this value, this is bigger than or equal to h of ys by the thing that I call triple star. But if you remember, there was this earlier thing that I called star, which said that for any rho bigger than a constant times h, the averages on y of k star were like 1. Okay, and then we're done. Okay, so that proves that one. All right, which is a good place to stop.